Okay, good morning. Today's lecture will be on symmetrical pure bending. Okay, so there's a question, when will we get your marks back? You'll get your marks on Monday. Okay, right. Let's go into symmetrical bending. So if we have a structure, okay, so I'm going to draw a structure now. So this is again for pure bending. So if we have a structure, or when we have a structure, okay, and then we have a pin on one side, and the other side is supported with a roller, okay, and then we have point A on one side, on the other side is point C, and then at point B we have a load applied in the center, okay, and this load is known as P. So we have our respective distances. So this is L over 2. Likewise, this is L over 2. Okay. So if we look at this structure, we know based on displacement is we will to draw our transformation. This is X, this is Y, and then we have rotation about Z. In terms of movement, okay, what we have is at point A, we know that it's under a pin, right? So when that's the case, the displacement in the X direction is equal to 0. The displacement in the Y direction is equal to 0. Okay. So whenever we restrict motion, there will be a reaction. I repeat again, whenever we restrict motion, there will be a reaction. So i.e., at point A, you have a reaction which is AY, and then you have a reaction over here which is AX. Okay. Then at point C, we have a roller, okay, a roller holding, right? So on a roller holding, what we have or support is X, the displacement is not equal to 0, right? So why the displacement is equal to 0? On the roller, we know that in the X direction, right, it can move in the X direction. It can slide left and right, okay? So in the Y direction, however, the movement is equal to 0. So whenever we restrict a motion, we have a reaction over here. So this is known as C in the Y direction. Anyone, any questions with this first? Anyone? Are we all clear with this? Okay, so I don't have any questions. So now I have a question for you guys then. Where will the structure fail? Anyone? Is it going to fail at point A? Is it going to fail at point B? Or is it going to fail at point C? Anyone, please?
At the joint.
Say it again.
At the joint.
At the joint. There's no joint over here.
Point B.
Yep. So we know, well done, okay? We know that failure will occur at point B. Okay, we are aware of that. So what is this failure due to? Okay, what is this failure due to? It can be due to two things. Okay, the first one, which we have just been through for 2 weeks, is we have the shear. Okay, we calculate the shear stress xy is equal to minus, not minus, is equal to by over, right, izz qz multiply divided by t, right? So we know this formula, right? We are aware of this formula. You guys know how to use it. Okay, you guys know how to apply it. Okay, you guys did both when it's a thick beam and when it's longitudinal shear, i.e. when it's made of several members. Okay, so that you know already. Okay, so the stresses can be induced due to shear, and for this case, what we are teaching today, the failure can also be due to bending. So this is due to shear force. Okay, later on, most of you know how to construct shear force diagram by now. Okay, so what we have now, the next mode of failure is due to normal stress. Okay, so normal stress. Okay, and the normal stress we are calculating is normal stress in the x direction. Okay, so later on I'll elaborate what we mean by normal stress in the x direction. But this time, watch the formula. Okay, what we have over here is equal to minus moment about the z-axis. Okay, divide by ixx. Sorry, moment about z. So divide by izz multiplied by y. Okay, so that is our bending moment equation. So the failure over here is caused by bending moment. Okay, is caused due to bending moment. So stress X corresponds to the normal stress in the X direction. And then IZZ is the second moment of area, which you guys know how to calculate. Okay, second moment of area. About the z-axis. Okay, so stress X, sorry, the units can be in Pascal or it can be in PSI. And the IZZ can be in meter to the power 4 or inches to the power 4. You guys know this by now. And MZ correspond to the applied moment right? Applied moment about the Z direction. Okay, and then the units is in Newton meter or pound inch. And then we have Y. So this Y over here is the Y distance. Okay, Y distance from the neutral axis. Okay, so it's in meters or in inches. Okay, so oops, do apologize. So what we calculate down here, okay, what we calculate down here in terms of moment between in terms of stress X, this equation over here, okay, it calculates the something happened. Microsoft, it always does this. Okay, so what it does over here, this equation over here is very similar to the shear stress equation. Okay, so this calculate the distribution of the normal stress of stress X. Okay, it calculates the distribution. It is not just the average value. Okay, so what do I mean by average value? So average value, okay, so if you calculate the average value, which you all know, okay, average value is always force divided by cross-sectional area. Okay, this is where you calculate the what? Average value. Okay, so the equation that we have over here, where stress X is equal to minus mzy over izz, we are calculating the distribution. Okay. Likewise, when we were doing the shear force, okay, so we were also, okay, we will also calculate, okay, we are also calculating the distribution of the shear in XY direction. Okay. Anyone, any questions, please? Are we okay? Okay. I have no one asking me questions, so it means everyone is okay for now. Okay.
Eugene, I have one question.
Yes.
So for the applied moment, is there any specific like a position, or is it like spread out all the part?
I will go into that later. Okay.
Oh, okay, okay,
Okay,
alright.
I'll explain that more into detail. Okay. Right. So now let's look at how this equation can be applied. And as like before, I have made rules. Okay, that is easier for you not to make mistakes. Okay, so I've developed rules that when you apply, you can analyze the structure better. Okay, in terms of later on, we might even go into 3D structure or unsymmetrical bending. So now we are doing symmetrical. Later on, when we do unsymmetrical, it means you have bending moment in two different directions. Okay, so I'm gonna teach you, okay, what I learned by solving a lot of problems. Okay, a trend. Okay, so now let's look at this structure now. Okay, so let's look at the structure that we've just drawn. Okay, that you see over there. So if you look at the deformation pattern, so we're going to look at the deformation pattern now. Okay, so we're going to look at deformation pattern. Okay, if we look at deformation pattern, right, and we realize that the root formula is equal to stress x is equal to minus moment about the z-axis divided by izz multiplied by y. Okay. Now the curious thing is this. Okay, the curious thing is this. You have a what? You have a minus sign. Okay. Why this minus sign has to be there, right? You will be asking, why are we putting a minus sign behind? By the way, moments, the moment and the y are vectors. Okay. These two, okay, these two, I'm going to circle in different color. These two, okay, they are vectors. They have directions, not only magnitude, they have direction. So moment about z has direction, y displacement or y distance also has a what? Has a distance. Also they are vectors. They have positive and negative. Okay. So now, if we look at our deformation based on the structure that I've drawn earlier, okay, look at deformation pattern. So this is my x, and this is my y. So the deformation pattern that we get based on the loading that is under simply supported, and there's a load applied in the center, like what I showed earlier over there. Okay, so we have a deformation pattern that looks like this now. Okay, so we have a deformation pattern that looks like this. Okay, so this is our deformation pattern, and I'd like to introduce you to I would like to introduce you to a new term. Okay, over here, this line, chain line that I've just drawn is known. Okay, I need space. So this is known as our neutral axis. Okay, that is our neutral axis. So based on what I've just drawn, let me tell you what is this neutral axis. Okay, so the neutral axis, so at the neutral axis, okay, the normal stress or the stress x, okay, the stress in the x direction will be equal to 0.